Most people think AI's energy problem is a technical issue. It's not. It's an incentive system reset. Hi, I'm Bevis Lee. With a background in engineering and EU market strategy, I analyze how infrastructure shapes business outcomes. In this video, I'll show you why energy is not limiting AI, but filtering who gets to compete. We'll break down the incentive conflicts between big tech, energy providers, and governments, and how this creates a new kind of barrier to entry. Because in the next decade, the key question is not how much power AI uses, but who controls that power and where you sit in that system. Most discussions about AI and energy begin with a familiar framing. Energy is a constraint, a bottleneck, a technical limitation that slows down progress. This framing is technically correct, but strategically misleading. It assumes that the primary impact of energy scarcity is to reduce the speed of innovation. In reality, the more profound effect is not deceleration, but selection. AI is not being stopped by energy limitations. It is being filtered. To understand this, we need to shift from an engineering lens to an incentive system lens. In engineering, constraints are problems to be solved. In economics, constraints are mechanisms that shape behavior and determine participation. Energy, in the context of AI, functions as the latter. It is not merely a resource input. It is a gatekeeping variable embedded within the cost structure of computation. Historically, when a resource becomes structurally expensive or constrained, the system does not collapse. Instead, it reorganizes. Participants who can absorb or control that cost remain in the system. Those who cannot are gradually excluded. This is precisely what is beginning to happen in AI. Compute was once the primary bottleneck. Then came the rapid scaling of GPU production, cloud infrastructure, and distributed training architectures. Data followed a similar trajectory, with large-scale scraping and synthetic data generation reducing scarcity. Today, both compute and data, while still expensive, are accessible through intermediated platforms. Energy, however, is different. It is geographically bound, politically regulated, and capital-intensive to scale. This creates a structural asymmetry. When energy becomes a dominant cost driver, the system begins to favor actors who have either direct access to energy supply, long-term contractual control over pricing, or the financial capacity to absorb volatility. These are not characteristics of small startups or independent developers. They are characteristics of large, capital-rich organizations, primarily big tech firms, and increasingly sovereign-backed entities. Therefore, the energy problem in AI is not about whether AI can continue to advance. It will. The question is, who will be allowed to participate in that advancement? From a cost structure perspective, energy is moving from a secondary operational expense to a primary strategic variable. This shift transforms the competitive landscape. Instead of competing purely on model architecture or dataset quality, firms must now compete on their ability to secure stable, affordable energy inputs. This introduces a new dimension of competition, one that is less transparent, more capital-intensive, and significantly harder to replicate. This is why framing energy as a technical barrier is insufficient. A technical barrier can, in principle, be solved and removed. An incentive filter, however, does not disappear when solved. It simply moves. Even if energy efficiency improves, the absolute scale of AI demand continues to grow. The filter remains in place, continuously selecting for actors with superior resource access. In practical terms, this means that the future AI landscape will not be defined solely by innovation, but by stratification. There will be tiers of participation. At the top are firms that control both compute and energy. Below them are firms that rent compute, but are exposed to energy pricing through cloud providers. At the bottom are actors who rely entirely on external platforms, with minimal control over cost structures. This stratification has direct implications for entrepreneurship. Many founders still operate under the assumption that AI is a democratizing force, that access to models and APIs lowers barriers to entry. While this is partially true at the application layer, it ignores the upstream concentration of power. As energy becomes embedded in pricing models, the cost of using AI services will increasingly reflect underlying energy constraints. In other words, democratization at the surface can coexist with concentration at the infrastructure level. For operators, the key strategic shift is to recognize that AI is no longer just a software layer. It is an infrastructure-dependent system. And infrastructure, by definition, is unevenly distributed. The implication is clear. Energy is not just a cost. It is a filter that determines who can scale, who can compete, and ultimately who can remain in the game. To understand the current AI energy dynamic, it is necessary to place it within a historical context. Energy has always played a foundational role in shaping economic structures, but its impact is often underestimated because it operates at the infrastructure layer, largely invisible until it becomes constrained. Consider the 1973 oil crisis. This event did not merely increase fuel prices. It fundamentally altered the global economic order. Energy importing countries experienced inflationary shocks, industrial slowdowns, and strategic vulnerability. In response, governments restructured their energy policies, diversified supply sources, and invested in efficiency improvements. Entire industries, such as automotive manufacturing, shifted towards smaller, more fuel-efficient vehicles. The competitive landscape was redrawn, not because technology changed overnight, but because the cost structure of energy forced adaptation. Moving forward to the 1990s, the liberalization of electricity markets introduced a different kind of transformation. By opening energy markets to competition, governments aimed to increase efficiency and reduce prices. This led to the unbundling of generation, transmission, and distribution, creating new business models and investment opportunities. However, it also introduced volatility and complexity into pricing mechanisms. Companies that could navigate these markets effectively gained a competitive edge, while others struggled with uncertainty. Then came the 2000s, marked by the rise of cloud computing. At first glance, cloud computing appears to be a purely digital innovation. In reality, it was deeply dependent on energy infrastructure. Data centers required massive amounts of electricity, but by centralizing compute resources, cloud providers achieved economies of scale. They could negotiate better energy contracts, optimize cooling systems, and distribute workloads across regions to minimize costs. This allowed them to offer computing power as a service, effectively abstracting energy costs away from end users. Each of these historical moments shares a common pattern. A shift in energy cost structure leads to a reallocation of economic power. The current AI energy situation follows the same pattern, but with greater intensity. Unlike previous transitions, AI introduces a compounding effect. As models become more advanced, their energy requirements increase non-linearly during training and linearly during inference at scale. This creates a dual pressure: high upfront energy costs for development and sustained operational costs for deployment. Moreover, the scale of AI adoption amplifies the impact. While the oil crisis affected transportation and manufacturing, AI affects virtually every digital service. From search engines to recommendation systems, from financial modeling to healthcare diagnostics, AI is becoming a foundational layer of modern economies. This means that any constraint at the energy level propagates across multiple sectors simultaneously. Another key difference is the speed of change. Historical energy transitions unfolded over decades. The AI revolution is unfolding over years, if not months. This compressed timeline reduces the ability of infrastructure to adapt. Power grids, energy generation facilities, and regulatory frameworks are not designed for rapid scaling. As a result, mismatches between demand and supply become more pronounced. This mismatch creates opportunities and risks. On one hand, companies that anticipate these constraints can position themselves advantageously by securing long-term energy contracts, investing in renewable generation, or optimizing energy efficiency. On the other hand, companies that ignore these dynamics may find themselves constrained by rising costs and limited capacity. From a strategic perspective, the lesson is clear. Energy is not a background variable. It is a primary driver of competitive advantage. For AI-focused businesses, this means that historical analogies are not just academic, they are predictive tools. The same mechanisms that reshaped industries during the oil crisis and the rise of cloud computing are now at play in the AI era. The difference lies in scale, speed, and integration. Energy is no longer just an input, it is an organizing principle. Understanding this allows operators to move beyond reactive thinking and adopt a more proactive stance. Instead of asking how to reduce energy costs, the more relevant question is how to align business models with evolving energy structures. This may involve choosing locations with favorable energy policies, designing products that minimize inference costs, or forming partnerships that provide access to stable energy supply. In essence, history does not repeat itself, but it rhymes. And in the case of AI and energy, the rhyme is unmistakable. When energy cost structures shift, power structures follow. At the core of the AI energy problem lies a structural issue that is often overlooked: incentive misalignment. While most discussions focus on supply shortages or technological limitations, the deeper friction emerges from the interaction between three key actors: big tech, energy companies, and governments. Each operates under a fundamentally different objective function, and these objectives are not naturally compatible. Big tech firms, such as Microsoft or Google, are driven by scale economics. Their goal is to minimize the marginal cost of computation while maximizing performance and user adoption. In practical terms, they require energy that is cheap, stable, and predictable over long time horizons. Volatility in energy pricing directly translates into volatility in AI operating costs, which undermines their ability to scale services profitably. Energy companies, by contrast, are capital-intensive entities that optimize for return on investment. Their business models depend on pricing power, capacity utilization, and long-term infrastructure amortization. From their perspective, AI-driven demand is an opportunity to increase prices, not reduce them. High demand from data centers allows them to justify new investments in generation capacity, but only if they can secure favorable pricing structures. Governments introduce a third layer of complexity. Their objective is not profit or scale, but stability and sustainability. They must balance economic growth with environmental constraints, particularly carbon emissions. This often results in regulatory frameworks that impose limits on energy production, incentivize renewable sources, or introduce carbon pricing mechanisms. While these policies are rational from a societal perspective, they can conflict with the needs of both big tech and energy providers. The result is a triangular conflict. Big tech wants low-cost, high-reliability energy. Energy companies want high-margin, demand-driven pricing. Governments want reduced emissions and system stability. These objectives cannot all be satisfied simultaneously. This misalignment creates systemic friction that manifests as delays in infrastructure development, pricing disputes, and regulatory uncertainty. For example, a government may restrict the construction of new fossil fuel plants to meet climate targets, while renewable capacity is not yet sufficient to meet AI-driven demand. Energy companies, facing regulatory constraints, may hesitate to invest in new capacity without guaranteed returns. Meanwhile, big tech firms face increasing costs and limited expansion options. This is the real Achilles' heel of AI. Not a lack of energy per se, but a lack of coordinated incentives. From a systems perspective, this misalignment introduces inefficiency. Resources are not allocated optimally, because each actor is optimizing for a different metric. This leads to underinvestment in some areas, overpricing in others, and overall instability in the system. For operators and strategists, the implication is significant. Success in AI is no longer determined solely by technical capability. It increasingly depends on the ability to navigate this incentive landscape. Companies that can align themselves with at least one of these actors, through partnerships, contracts, or regulatory positioning, gain a structural advantage. For example, securing long-term power purchase agreements, PPAs, can mitigate price volatility. Investing in on-site renewable generation can reduce dependence on external suppliers. Engaging with regulators to shape favorable policies can create additional leverage. In contrast, companies that remain purely at the application layer, without considering upstream dependencies, are exposed to the full impact of this misalignment. They become price takers in a system where they have no control over the key cost driver. In conclusion, the AI energy problem is not a simple supply-demand imbalance. It is a multi-actor system with conflicting incentives. Understanding this structure is essential for anyone seeking to operate at scale in the AI economy. The evolution of AI economics can be understood as a sequence of cost layer transitions. Initially, the primary constraint was labor, human expertise required to design, train, and deploy models. With the rise of automation and standardized frameworks, this constraint shifted toward compute. GPUs, cloud infrastructure, and distributed systems became the dominant cost drivers. We are now entering the next phase, the transition from compute to energy. This transition is not merely a shift in cost categories. It represents a fundamental change in how value is created and captured within the AI ecosystem. Compute, while expensive, is scalable through manufacturing and capital investment. Energy, however, is constrained by physical infrastructure, geographic distribution, and regulatory frameworks. To understand the implications, consider the unit economics of AI. At the training stage, energy consumption is highly concentrated. Large models require massive computational resources over relatively short periods. This results in high upfront costs, but these costs are amortized over the lifetime of the model. At the inference stage, the dynamic changes. Inference is continuous and scales with usage. Every user query, every API call, every interaction consumes energy. Unlike training, which is episodic, inference represents a persistent operational cost. This is where the transition becomes critical. If inference costs cannot be reduced sufficiently, the economic model of AI begins to break down. The promise of AI lies in its ability to scale non-linearly, serving millions or billions of users with marginal costs approaching zero. However, energy introduces a linear component to this equation. Each additional unit of usage incurs an incremental energy cost. This creates a tension between scalability and sustainability. In theory, improvements in hardware efficiency and algorithm optimization can offset some of these costs. In practice, however, demand growth often outpaces efficiency gains. As AI applications become more sophisticated and widely adopted, total energy consumption continues to rise. This leads to a phenomenon we can describe as scaling friction. Scaling friction occurs when the cost of serving additional users does not decrease as expected. Instead, it stabilizes or even increases due to underlying resource constraints. In the context of AI, energy is the primary source of this friction. The implications are far-reaching. First, business models that rely on high-frequency, low-margin interactions become less viable. If each interaction carries a non-negligible energy cost, profitability depends on pricing power or cost optimization. This may lead to increased monetization pressure, such as subscription models or usage-based pricing. Second, the location of infrastructure becomes more important. Data centers may be built in regions with abundant and cheap energy, leading to geographic concentration. This, in turn, introduces latency, regulatory, and geopolitical considerations. Third, the competitive landscape shifts toward firms that can manage energy costs effectively. This includes not only large technology companies, but also energy producers and infrastructure providers. From a strategic perspective, the compute-to-energy transition requires a rethinking of priorities. Efficiency is no longer just a technical metric, it is a core business parameter. Designing models that deliver acceptable performance with lower energy consumption becomes a key differentiator. Moreover, companies must consider energy as part of their core strategy, not an external factor. This may involve investing in energy infrastructure, forming partnerships with energy providers, or developing proprietary technologies to reduce consumption. In summary, the transition from compute to energy marks a new phase in the evolution of AI economics. It introduces new constraints, new opportunities, and new competitive dynamics. Understanding this transition is essential for navigating the next decade of AI development. When incentives are misaligned and costs become structurally significant, rational firms do not wait for the market to stabilize. They move upstream. This is exactly what we are observing in the behavior of major technology companies. Consider Microsoft. Its exploration of nuclear-linked energy solutions is not a public relations gesture. It is a direct response to a predictable future where energy availability constrains compute expansion. Nuclear energy offers one key advantage: stability. Unlike renewables such as solar or wind, it provides consistent baseload power, which is essential for data center operations that cannot tolerate downtime. Similarly, Google has been aggressively securing long-term energy contracts, including experimental agreements related to next-generation energy technologies. The logic here is financial, not environmental. By locking in energy prices over long horizons, Google reduces exposure to market volatility and gains cost predictability, both critical for scaling AI services. Meta Platforms takes a slightly different approach, focusing on hyperscale data center construction, optimized for energy efficiency. By designing infrastructure from the ground up, Meta can control not only compute performance, but also energy consumption per unit of output. This is a form of operational vertical integration. What unites these strategies is a common principle: control the constraint. This behavior is not new. It mirrors historical patterns in other industries. A useful analogy is Amazon building its own logistics network. Initially, Amazon relied on third-party carriers. As scale increased, logistics became a bottleneck, costly, unreliable, and outside its control. The solution was to internalize the function. Today, Amazon operates one of the most sophisticated logistics systems in the world. Energy is becoming the logistics problem of AI. The implication is that energy is no longer an externality. It is a strategic asset. Companies that can secure, control, or influence energy supply gain a structural advantage that is difficult to replicate. This shifts competition from purely technological domains into infrastructure domains. For smaller firms, this presents a challenge. Vertical integration into energy is capital-intensive and often requires regulatory approval. It is not a viable option for most startups. As a result, they remain dependent on platforms that have already secured energy advantages. This dependency has second-order effects. Pricing power shifts toward platform providers. Innovation may become constrained by access to affordable compute, and the gap between large and small players widens. From a strategic standpoint, the key insight is that vertical integration is not optional at scale. It is inevitable. The question is not whether companies will integrate energy into their operations, but how and to what extent. For operators, the actionable takeaway is to recognize where you sit in this structure. If you cannot control energy supply, you must design around it. This may involve optimizing for efficiency, choosing the right platform partners, or focusing on business models that are less energy-intensive. In summary, the current moves by big tech are not isolated initiatives. They are early indicators of a broader structural shift. Energy is moving from the periphery of strategy to its core. Discussions about AI energy often remain abstract, but the scale becomes clearer when translated into numbers. These figures are not merely illustrative. They reveal the structural limits that define the power wall. Training a frontier AI model requires an extraordinary concentration of energy. Estimates suggest that a single large-scale training run can consume electricity equivalent to hundreds of households over an entire year. While exact figures vary depending on architecture and hardware efficiency, the order of magnitude is consistent. Training is energy-intensive, capital-heavy, and episodic. However, focusing solely on training can be misleading. The more critical component is inference. Unlike training, which occurs intermittently, inference happens continuously. Every time a user interacts with an AI system, whether through a chatbot, recommendation engine, or automated workflow, energy is consumed. This consumption scales linearly with usage. This creates a fundamental economic dynamic. At small scale, inference costs are manageable. At large scale, hundreds of millions or billions of users, they become dominant. Even marginal increases in per-query energy consumption can translate into massive aggregate costs. This is the essence of the power wall. The term power wall describes a situation where further scaling is constrained not by computational capability, but by the availability and cost of energy. In semiconductor design, a similar concept emerged when increasing clock speeds led to unsustainable heat generation. In AI, the constraint is not heat alone, but the entire energy supply chain. As AI adoption accelerates, demand for electricity from data centers is projected to grow significantly. Some estimates suggest that data centers could account for a substantial share of global electricity consumption within the next decade. While projections vary, the trend is clear. AI is becoming a major energy consumer. This introduces several constraints. First, infrastructure limitations. Power grids are not designed to accommodate rapid, localized increases in demand. Building new generation capacity and upgrading transmission networks takes time, often measured in years or decades. Second, cost constraints. As demand increases, energy prices may rise, particularly in regions with limited supply. This directly impacts the operating costs of AI systems. Third, environmental constraints. Increased energy consumption raises concerns about carbon emissions, leading to regulatory interventions that may further restrict supply or increase costs. From a business perspective, these constraints translate into risk. Companies that fail to account for energy costs in their models may find their margins eroded as scale increases. Conversely, companies that optimize for energy efficiency or secure favorable energy contracts can maintain or even improve profitability. The key insight is that energy is not a secondary consideration. It is a scaling variable. In practical terms, this means that every AI application should be evaluated not only in terms of performance and accuracy, but also in terms of energy consumption per unit of output. Metrics such as energy per inference become as important as latency or throughput. In conclusion, the numbers behind AI energy consumption are not just large, they are structurally significant. They define the boundaries within which AI can scale. Understanding these boundaries is essential for making informed strategic decisions. As energy becomes embedded in the cost structure of AI, it transitions from an operational concern to a strategic asset. This shift has direct implications for competitive dynamics, particularly in terms of barriers to entry and market concentration. Traditionally, the primary barriers to entry in AI were technical. Companies needed access to advanced algorithms, high-quality data, and specialized talent. While these factors remain important, they are increasingly complemented, and in some cases overshadowed, by a new barrier: energy access. Energy access is not evenly distributed. Large technology firms have the financial resources, scale, and bargaining power to secure favorable energy arrangements. They can negotiate long-term contracts, invest in dedicated infrastructure, and influence regulatory frameworks. Smaller firms, by contrast, typically rely on market rates and shared infrastructure, making them more vulnerable to price fluctuations. This creates an asymmetry. In economic terms, asymmetry leads to the formation of moats, defensible advantages that protect incumbents from competition. In the context of AI, energy becomes such a moat. It is difficult to replicate, requires significant capital, and is often tied to physical and regulatory constraints. The existence of an energy moat has several implications. First, it reinforces platform dominance. Companies that control both compute and energy can offer services at lower effective costs, attracting more users and developers. This creates a feedback loop. More users generate more data and revenue, which can be reinvested into further infrastructure, strengthening the moat. Second, it limits the scalability of independent players. Startups may be able to innovate at small scale, but as they grow, they face increasing exposure to energy costs. Without access to preferential pricing or dedicated infrastructure, their margins may be compressed. Third, it introduces geopolitical considerations. Energy resources are geographically distributed and subject to national policies. This means that the location of data centers and the jurisdiction of operations can influence competitiveness. Countries with abundant, cheap, and stable energy may become hubs for AI infrastructure. From a strategic standpoint, companies must recognize that competing in AI is no longer just about building better models. It is about positioning within an energy-constrained system. For operators, this means asking different questions. Instead of focusing solely on technical differentiation, consider how your business model interacts with energy costs. Are you exposed to usage-based pricing? Can you optimize for efficiency? Do you have access to favorable infrastructure? In some cases, the optimal strategy may be to align with existing platforms rather than compete directly. In others, it may involve targeting niches where energy consumption is less critical. In all cases, the underlying principle remains the same. Energy is a constraint that shapes competition. In summary, the emergence of energy as a moat marks a new phase in the evolution of AI markets. It reinforces existing hierarchies, introduces new forms of asymmetry, and requires a shift in strategic thinking. For entrepreneurs and small to medium-sized enterprises, the implications of AI's energy constraints are not abstract. They directly affect decision-making. The key challenge is to determine whether a given AI application is viable within an energy-constrained environment. A practical starting point is to classify AI applications based on their cost structure. The first category is training-intensive applications. These involve significant upfront investment in model development, but relatively lower ongoing inference costs. Examples include specialized models trained for niche tasks. For these applications, energy costs are concentrated and can be planned for, making them more manageable. The second category is inference-intensive applications. These rely on frequent, large-scale interactions with users. Examples include chatbots, recommendation systems, and real-time analytics platforms. In these cases, energy costs scale directly with usage, making them more sensitive to pricing and infrastructure constraints. This distinction is critical. Inference-intensive models are more exposed to the power wall. As usage grows, so do costs. Without sufficient efficiency or pricing power, profitability becomes difficult to sustain. Therefore, the go-no-go decision should incorporate energy considerations alongside traditional factors such as market demand and technical feasibility. Key questions include: what is the energy cost per inference? How does this cost scale with user growth? Can efficiency improvements offset cost increases? What is the pricing model, and does it cover energy expenses? Which platform or infrastructure provider will be used, and what are their energy dynamics? In addition to application design, platform choice becomes a strategic decision. Different cloud providers have different energy efficiencies, pricing structures, and geographic footprints. Selecting a platform with optimized infrastructure can significantly reduce costs. Another consideration is architectural design. Techniques such as model compression, caching, and hybrid approaches, combining AI with rule-based systems, can reduce energy consumption. These optimizations may not be as visible as model accuracy improvements, but they have direct financial impact. From a broader perspective, the decision framework must shift from a purely growth-oriented mindset to a constraint-aware mindset. Growth is no longer unlimited. It is bounded by underlying resource availability. This does not mean that opportunities are reduced. On the contrary, constraints often create new opportunities. Applications that deliver high value with low energy consumption may become more attractive. Efficiency becomes a competitive advantage. For operators, the key is to integrate energy considerations early in the design process. Retrofitting efficiency after scaling is significantly more difficult and costly. In conclusion, the go-no-go logic for AI applications must evolve. Energy is no longer an external factor. It is a core variable that determines viability. Incorporating this perspective enables more informed, resilient decision-making. Energy is often described as a resource, an input, or a cost. In the context of AI, it is something more fundamental. It is a mechanism of control. To understand this, consider the relationship between cost structures and participation. In any economic system, the ability to control key cost drivers translates into the ability to influence who can compete. When energy becomes a dominant cost in AI, controlling energy effectively means controlling access to AI capabilities. This is why the energy discussion is not merely technical, it is political and structural. Control over energy supply determines pricing. Pricing determines accessibility. Accessibility determines participation. And participation determines the distribution of power within the system. This chain of influence transforms energy from an operational variable into a strategic lever. For large organizations, this lever can be actively managed. Through investments, partnerships, and policy engagement, they can shape their energy environment. For smaller actors, however, energy is often an external constraint, something to be managed rather than controlled. This asymmetry leads to a concentration of power. As energy becomes more tightly integrated with AI infrastructure, those who control energy resources gain disproportionate influence over the direction of technological development. This influence extends beyond economics into areas such as regulation, standards, and even geopolitics. From an operator's perspective, the critical question is not, how much energy will AI consume, but who sets the price of that energy, and where do I sit in that system? This question reframes strategy. Instead of focusing solely on building capabilities, operators must consider their position within a broader network of dependencies. Are you upstream or downstream? Are you a price maker or a price taker? Do you have leverage, or are you exposed? These considerations may not be visible in early-stage decision-making, but they become increasingly important as scale increases. The key insight is that energy defines the boundaries of the system. Within those boundaries, innovation can flourish. Outside them, participation becomes unsustainable. Therefore, energy is not the endpoint of AI development, it is the starting point of the next phase. A phase where incentives are restructured, roles are redefined, and power is redistributed. In closing, the AI revolution is often framed as a story of algorithms and data. This is only part of the picture. The deeper story is about infrastructure and control. And at the center of that story is energy. Control energy, and you control the cost structure. Control the cost structure, and you control the game.